Hi folks, welcome back to the difference quotients videos. We're in our second video. And in this video, we're going to take a look at two examples that are a little bit different looking than the ones we took a look at in the first one. Now, the idea is still the same. We're looking for slope. And in fact, we're looking for slope at a specific point, okay? And so let's go ahead and get started using our formal definition of a derivative to find the slope of this function. F of x equals the square root of x, all right? So the very first thing we're going to do is we're going to say f prime of x equals the limit as h approaches 0. Remember, we always have to write this part of f of x plus h minus f of x over h. Okay, now this is just our definition, but we want to keep in mind that our f of x in this case is now the square root of x. And so if I wanted to sort of prep myself mentally, f of x plus h would be everywhere I see an x, I'm going to replace it with an x plus h. So underneath the square root would be x plus h. Okay, so I'm going to go ahead and plug in square root of x plus h in for the f of x plus h. I'm going to go ahead and plug in square root of x for f of x, and let's see where we get. All right, the limit as h approaches 0 of the square root of x plus h minus the square root of x over h. Now, if I plug in 0 at this point, what I'm going to find is that is that this part is going to be fine. It's just going to be square root of x. But then on the bottom, we're going to have an h. That is the problem, right? Because when we divide by 0, we get an undefined situation. So this is the reason why we're going to have to try a little bit of some algebra to get it into a form where it's going to be okay to plug in 0 for h, okay? All right, so our trick for things with a square root, all right, is as follows. We're going to multiply by a fancy one. Okay, now we've used this idea of a fancy one before, but we're going to multiply by a fancy one in a very specific way. It's going to look really similar to what we have in our numerator. Okay, however, instead of a minus sign, we are going to have a plus sign. Okay, instead of the minus sign, we're going to have the plus sign. What we've done now is we're multiplying by a fancy one, but in particular, this fancy one happens to have it happens to be a conjugate of the numerator we already have. Okay, now here's the reason why we're going to do this. We're doing this so that we're going to be able to get rid of some square roots in a way that's going to help us cancel some stuff out. Okay, so here we go. Limit as h approaches 0. And now we're going to go ahead and multiply the top and bottom, or the tops and the bottoms. So we have square root of x plus h minus square root of x times square root of x plus h plus square root of x. And then on the bottom, I have h times square root of x plus h plus square root of x. Now, one thing I notice is that sometimes students get to this stage and they're like, oh, well, Judy, these two cancel out, right? And that's true, but if you cancel them out, you're going to get right back where you started. So although it's mathematically accurate to do that, probably not the best decision to go forward here, right? Instead, what we're going to do is we're going to go ahead and we're going to FOIL out the top, but we're going to be patient and we're going to leave the denominator the way it is. All right, so my denominator is still going to be this, okay? But my numerator, let's see what happens when I FOIL. First terms multiplied together, square root of x plus h times square root of x plus h will just give me x plus h. Then my outer terms, I have square root of x plus h times square root of x, and that will give me plus square root x plus h. And I know that looks gross and uncomfortable, and maybe we're thinking, well, do we need to simplify it? How do we simplify it? And our brains start going off in a way that maybe isn't helpful for us, okay? So here's where I'm going to ask you to be a little patient with me. So we're taking the outer terms, we're multiplying them, we get this. Now let's take our inner terms and multiply them, and look at what we get. Negative square root of x plus h. Okay. Now we take our last terms, negative square root of x times positive square root of x gives me minus x. Now, the reason why I said let's not worry about how we simplify the outer and inner terms is because they're exactly the same. And so at this point, positive and negative versions, those go to 0. And so instead, my numerator is this. Limit as h approaches 0, x plus h minus x all over our denominator. Okay. Now we might again see x and x are going to go away, right? So let's add those. X plus negative x goes to 0. But what else goes away now? I actually have a plus h and an h here. This h, let's get a different color here. This h and this h, they reduce. And so what do we have left? The limit h approaches 0 of 1 over square root of x plus h plus square root of x. All right. Now, remember, our very last step is now we plug in 0 for h. Because when we plugged it in the beginning, that's the whole idea behind what we wanted to do, plug in 0 for h. It was a problem because we had to divide by 0, and we're not allowed to do that in mathematics. So now let's see. We've used a little bit of algebra. What happens now when we plug in 0 for x, or for h? Okay, so now that I'm plugging in 0, I don't write the limit anymore. 1 over square root of x plus 0 plus square root of x equals 1 over square root of x plus square root of x. Those are like terms, so I really have 1 over 2 square root x. Okay, so there it is for you all on one page. When we take a look at the square root function or radical function, we have to have a slightly different approach than we did with the linear function and with the quadratic, okay? All right, we're going to do one more example in this video, and that is going to be taking a look at an example where we have a rational function, okay? So another important family of functions. Now we have 3 over x instead of just something like 3x. So first things first, f prime of x equals the limit as h approaches 0. Now I want f of x plus h. So everywhere I see an x, I'm going to put an x plus h minus f of x all over h, right? That's just plugging things into the definition. Now, when I plug in 0 for h, though, gives me that same old problem. I'm going to divide by 0, no good. So we've got to do a little bit of work. And in this case, we see that we have two different fractions. And so the strategy we're going to use here is to combine those into a single fraction. And when we combine things into a single fraction, we have to have a common denominator, okay? So let's get started finding this common denominator. So I'm going to do two things at once, okay? I'm going to take this h in the denominator, and I'm going to pull it out in front. So it's really like times 1 over h. And then I have my fractions, 3 over x plus h minus 3 over x. And if I want them to have a common denominator, I have to think about what I multiply them by. This one I'm going to multiply by x over x. And the second one I'm going to multiply by x over h times x over h. Because now x times x over x plus h is the same as x times x plus h. I have a common denominator. We're good to go. Okay. Now I could write all of this all over h instead of having my 1 over h in the front, but I think sometimes that gets very visually overwhelming. It's just so many fractions, and it makes it easier for some brains if we pull the 1 over h out to the front. But I'll leave that up to you, okay? So if you don't have a problem with doing all of this over h, you're fine to keep it that way as well, okay? All right, let's do some algebra. Limit as h approaches 0, 1 over h, I get 3x minus 3 times x plus h all over x times x plus h. All right, so I've combined my fractions, and now I want to be really careful that I distribute this -3 to the x plus h. And so I know it's kind of boring, but yes, every single time you've got to write the limit as h approaches 0. If you don't write that, it means you've used it already, and I don't think we've used it yet. So 3x minus 3x minus 3h all over x times x plus h. All right, let's see what we have. The limit as h approaches 0. I notice that the 3 x's reduce. This h and that h reduce, and I end up with -3 over x times x plus h. Okay. So remember, at the beginning, we said, let's plug in 0 for h, and if we can solve it, we can solve it. But one thing I notice is when I plug in 0 for h now, I don't have that annoying 0 only in the denominator, okay? So what happens if we plug in h? Well, first of all, we don't write limit as h approaches 0 anymore. We just go ahead and plug in 0 everywhere we see the h. This gives us -3 over x times x, which is x squared. And there you go. That function, -3 over x squared, will actually tell you the slope of 3 over x at every single point that you're interested in, okay? And it will tell you where you might not have a slope for the function, okay? So it tells you a lot of information. All right, my friends, we're going to end there. I hope you've learned a little bit about that difference quotient, going to be a super important thing as you go into your calculus class here. And I'll see you later.